I assume we have reviewed good enough for probability and conditional probability. One thing I want to emphasize is, or mention, not emphasize, is the Bayes rule. I think all of you have done some exercise, homework for Bayes rule, right? Bayes rule did not add any new information beyond the conditional probability we just introduced, okay? So if I know, it's basically how to do conditional probability of B given A, which is probability of B intersect with A. What's it? Let's see. Divide by A, right? And because of, so you know, let's see this. Okay, sorry. So you know that probability B intersect A is nothing but probability of B given A times probability of A, right? So we can relate this guy to probability B given A. So that's what? So you can say this is probability of A intersect B. Let me use the other one, sorry, which is probability of A given B times probability of B divided by probability of A, right? Well, these two are the same. You can swap the order of doing conditional to doing conditioning. Okay, so all of these are following probability axioms as well as the definition of the conditional probability. Once the definition is specified, this rule is completely specified. There's nothing to to memorize too much. So basically, these two are related by this formula. Okay, and the two events are called independent. It's not linear independent. It's statistically independent. If what? You may have heard of this, right? Probability A and B equal to probability A times probability B. Why? This is not the most direct definition. The direct definition of independence is this. Okay? So probability of A given B has to be probability of A. So knowing B occurred or not does not change your belief about randomness inside A. So they are independent. Tell me this guy occurred doesn't mean anything. Okay, so the reason is also you can follow that from. So if this is the case, A intersect B is probability B given A times probability of B, right? That's from the formula we had before. And if this is the case, that's become A times B. Okay, so this one is a consequence of this more direct definition of independence. So sometime I will say A orthogonal to B. All right, that's independent statistically. All right, now let's jump to this very basic introduction to probability, a short review with emphasis of the conceptual ideas behind defining probability and modifying probability after you know some event has occurred. Okay, so next we are going to discuss about random variables and a little bit jump to random vectors. You must not have not heard about random vectors, right? What's the difference between random variable and random vectors? No difference. What's the difference between scalar and vector? Scalar is R1 vector. Okay? So you just need to be a little bit more open to the new terminologies. There is essentially no fundamental difference. Before that, I want you to really remember the following things, okay? I always be asked about when I say something deterministic variable or deterministic constant, let's say, or a random variable. What's the difference? What is a deterministic variable? So I would say, for example, I say A is deterministic. Let's not use A. Sorry. Let's say Z is a deterministic variable. Does that mean I know what Z is? It could or may not. Okay. It's just say I said this is a variable. I don't know its value, but it's deterministic. What do I really mean? Z, actual deterministic, means it can only take one value. Actually, it's a single value, okay? Variable. Okay? Can only take one possible value. Too many comments, okay? Okay. Which may or may not be known. Whether I know this value or not does not matter, but I want to emphasize it is a single valued variable. It only takes one possible value. When I say deterministic in this class, I mean that. It could be 2, could be 3, could be R2 number, but it doesn't matter, it just takes one value. A random variable, can you define it for me? There is a when I take a probability theory from math department when I was a graduate student, defining what random variable is takes quite a long time. It's actually mapping from sampling space to some space. Okay, and you need to care about measurability. But for this undergrad level, let's just have the engineering definition. Okay, so it's a random variable. Random variable or vector. I don't distinguish between these two. Okay, to me, there's no just special meaning for scalar because everything is a special case of a vector. Okay, random variable or vector is multi-valued variable. Okay, what do I mean by that? It takes multiple, or even infinite, okay? Possible values. Each occur with certain probability. Is that clear? If I say X is random, it takes multiple values. Okay, it could take 1 or 2, but each of them occur with certain probability. Then this variable becomes a random variable. For example, I would say X is a random variable. It may take value 1 and 2, each with likelihood 0.5 and half. It's not a single value, it takes 2 values, right? Each of them occur with certain probability. Okay? Just could be as well like 1, 1. It could be R2. This guy is 30%. This guy happens with 70%. It becomes a random vector. Sounds harder, but essentially, do you think they are the same? It's just a point in R2 or in R1 or not. Okay? So X may take multiple values. Each of them occur or happens with certain probability. Those are the sentences I want you to memorize or remember. What's deterministic? it is a single valued variable, okay, which we know or may not know its value, okay? Random means it has so many possible values it can take. Each of them happens with certain probability. Okay. Or continuous. I'm going to specify that later, okay? Continuous random variable. So x may belong to 0 and 1, right? X could be a continuous variable. It takes all the possible values, real number between 0 and 1. Let's say this, okay? That's possible. And then each of those values occur with certain probability, but those probabilities may be, let's say this is 1, this is 0. So it may have some density function. That's so-called probability density function, PDF. Okay, so it takes how many values? Infinite, uncountable even, real numbers. And each of them occur with certain tiny bit of probability, mass or density. Okay, so that's become a random variable. So let's go back to how to specify a probability measure for a random variable. For discrete, it's very simple. It's just you need to specify, or it can be completely determined by the probability mass function, PMF. This is the most intuitive way to define probability. Suppose I want to toss a coin or die, let's say die. Okay, so omega is 1, 2, 3, 4, 5, 6. Okay, this is all the possible outcomes. Each element is one outcome. PMF, probability mass function, I need to define, let's say PI is the probability of the ith outcome. You just need to tell me this is the P of 1, this happens with P of 2. Each discrete value occurs with certain probability. You just need to specify this probability, then you specify everything you need. Because we know that this event space is empty 1, 2, 6, and 1, 2, 1, 3, right? All the way to 1, 2, all the way to 6, right? That's all the event I need to evaluate their probability for any A belong to this event space. So its measure, its probability measure, is induced by the probability mass function. I don't need to assign. I don't need to assign for each of them and list a table for you, okay? Because there's a natural way to define the probability of the event is probability of A becomes the summation I belong to A, P of I. The mass summing up together. You have learned all of this. I'm just asking you to follow the very basic framework of probability space to try to understand those things again. Okay? So in continuous time, summation becomes integration. Sorry, not continuous time, continuous variable. So you don't have a mass function, you have a probability density function. For example, suppose I have a temperature density. Suppose this is my temperature. This is maybe 27. Okay, and so maybe Shenzhen's temperature could be like this. So in this way, x belongs to R is a random variable. It's continuous. And the entire omega is R. If you know, of course, it won't be too low or too high, right? You can cut it off or just say it's R. And to specify the pure any event, okay, an event is subset of this, right? So event will be, let's say A is, for example, could be from 26 to 26.5. That's an event. Why? It's a subset of something space. Okay? For any event, I should be able to tell you a probability. How do I do it? We need probability density function, this guy. So this is our probability density function, f of x, x. Okay, so that's f capital X, small x. Let me briefly discuss my notation a little bit. In this class, in my notation, all right? Maybe this notation here I should mention first. So we typically use capital, typical, okay? Most of the time, now means always. Typically we use capital to denote random variables or vectors, lowercase to denote specific values the random variable takes. So this is a variable, random variable. It may take multiple values, right? In particular, it may take a value which we call x, small x. Let me repeat. Capital means a random variable. It takes multiple values. A small x is one specific value that I'm evaluating at, okay? So PDF is nothing but roughly what? It's not too low, but I would say quote unquote, probability of the random variable takes the small value x. Okay, the x could be 2 or 3 or 5 or 6, right? So it's a dummy variable representing a specific number. Now I will say probability of A. If I define the density, if I give you a density, then the probability of A is x belong to A, capital X, small x, dx. It's summing up all the possible outcomes probability. Okay? You should view this guy is the same as this integral, summing up the individual mass. If you have taken signal and systems, you know the delta function, right? This is almost integral of delta function to give you the summation of that number. Okay, so if you specify probability mass function for discrete or probability density function for continuous random variable, you basically specify all the uncertainties. Okay, for you, for modelers, you need to define this. You need to define this mass function or density function. After that, this becomes probability theory. As I mentioned, there's no right or wrong to say what the density function is, but after you specify it, later on, once you compute other things, you have to follow rules. Otherwise, you make very bad decisions, okay? Random vector, actually, I don't need to do that again. It's actually the same. As I mentioned before, it's the same, right? It's just it takes multiple values. Just this value now is Rn. Is instead of R, it's Rn. When you specify the probability of the random vector, you also need a density function. The only difference, I wouldn't call it a difference. Usually need to be used to this notation, fx doesn't mean this x is a scalar. If you can think about it as scalar is a special case of vector, then we are all set. Okay, in this case, x is nothing but x1, x2, all the way to xn is n-dimensional, right? And so this density function is nothing but, this is shorthand notation for with the formula you're more familiar with, x1, x2, xn. So these two means the same. It's either I write out explicitly all the coordinates, or I just write a simple variable x to denote the entire vector. All right. I just want to think about everything is just vector or scalar is fine. Random or not, that's the key difference. It's random if it takes multiple values. Each of them occur with certain probability. I start repeating this, right? So that means it's important. And this value could be scalar, could be a vector. You just need to sum them up for computing probability, okay? We use probability evaluation. Is still a probability of a event is nothing but integral over a. That means x belongs to this a dx. For example, if a is, for example, this is multidimensional. Okay, this is multidimensional integration. All right, so it can involve quite kind of a tedious multivariate calculus. Okay, I'm not going to talk. I'm not going to ask you to do this because I'm not good at multidimensional integration stuff. I never remember any formula from my calculus. The only thing matters is the definition. The formula are not important. Okay. I can give you an example. A could be x could be x1, x2. Okay, and a could be, say, belong to this times 3, 2. So R2 dimension. Then the integral will be, this is x1, this is x2. Sorry. So that will be from 1 to 2, and from 2 to 3, and fx, f, x1, x2, and dx2, let's say dx1. Things like that. It's just multidimensional integration. What essentially you're doing is just summing up all the likelihood that satisfies requirement specified by the event A. Okay, we got more exercise. I think this will become clear. Now we start to move. As I mentioned before, all we need, or the main thing we're targeted for, is conditional expectation, right? That's Kalman filter. Now finally we get to one keyword. Now it's called expectation. I need to ask you, what is expectation? 你说一下吧，什么是 expectation？ 期望。你学了什么就是做什么。一个结果，这样跟主题语言啊，忘了，期望怎么记得了吗？你说一下。期望怎么记得？加权平均，是吧？期望加权平均，期望应该是 probability the most elementary or most important concept for probability is the expectation or average or mean, right? So it's sometimes called mean of a random variable. It's by definition, it is this. Why is called 加权平均 weighted average? It's one number that represents this random variable or vector. Okay? What is number? How to compute this number? Weighted average. So you remember, okay, x is a random variable or vector. Then it takes what? Multiple values, each of them with certain probability. So which how do you represent this thing? You represent this, for example, one important characteristic is the weighted average of those values, right? You have so many values. If I say, what's the temperature today? It's a random variable. You can take many values. Suppose we didn't look at the app. Okay, you think it's certain range, right? Each of them with certain probability. And expectation is just the value it takes times the likelihood that value occurs, and then you sum them together will become expectation. Let me repeat again, okay? That's the thing you need to remember, not formula, just expectation you have to remember. Expectation for a random variable. A random variable takes multiple values. Each value occurs with certain probability, okay? So expectation is just the value it may take times the corresponding probability that value occurs. You sum them together, that gives you expectation. Well, in shorthand notation, it's just, in short, it was just a weighted average. And the weights are the probability that value occurs. Okay, so whenever you see this E of X, you always directly think, oh, the definition is just a integration. Why there's an integration? Summation is a special case of integration. You can think about this as a summation, right? Okay, it's a sum, weighted sum, right? Weighted average, weighted sum. That's where this comes from. Okay. In my notation here, I already generalized it. Okay. The formula looks the same as what you learned before, but the value could be a vector. Can you do an integration of Rn function? Yes, of course. Why not? Remember, this one is what? This is a scalar. It's a likelihood. It's a number. Okay? If the density doesn't mean it's between 0 and 1, but it's a density, right? So this guy is Rn, in Rn. You should be careful, right? So this is the value that capital X takes in Rn times the likelihood or probability, quote unquote, this value occurs. And this guy is exactly the same. I use different ways to explain. I never read this to you, okay? That's what I'm trying to do is explain. You should try to be able to tell me this as well. Okay, once you understand the definition, I think everything else becomes simple. For example, if X is Rn, okay, the expectation of the random vector actually is that you take individual expectations of its elements. Do you think this is a definition or a consequence of my early definition? This because of this, okay? You can derive this from the definition. For example, some people just was bothered by this. Let's say I have two-dimensional random vector. It has two elements. X1 and X2 are both random. And the combination of these two also random means what? It takes different values. Each of them occurs with different probability. Okay. So when I say expectation of X, can we do this? In your undergrad class, you can only do maybe one variable or two variable. If I do this, it's a vector. How do I do it? By definition. Is the definition defined for Rn? Yes, of course. So you just say, okay, then I will have R2. And all the possible values in R2 I can take. I enumerate them by X1 and X2. This is a vector, okay? And times the likelihood. X1, X2 equal, this is dx1, dx2. Okay? Inside the integration, you can think about them as a weighted sum. You just have a large number of two-dimensional vectors. Each of them have a probability constant as a weight, and you sum them together will give you another two-dimensional vector. All the things here is weighted sum of some two-dimensional vectors. This guy is a scalar, this guy is a vector, right? Eventually I will say my favorite word, verify yourself. You will have this guy is nothing but expectation of x1 and expectation of x2. I can give an example. Maybe that's a little bit easier to discuss or to see this from the discrete example. Let's say I have a R2, a discrete random variable with how many values this random vector takes. How many values this random vector takes? It's random, right? Random takes multiple values. How many possible values it takes? 3, right? It's basically, if you draw, maybe this takes some 3, only possible on these 3 dots, okay? So let's say, now I ask you to compute, first of all, what's the expectation of this? How to do this? This is a random vector now, okay? How to do this? By definition, that's the formal answer for almost everything I ask you. By definition, yes. How? X takes multiple values. Each of them occurs with certain probability. Then I need to sum them together as a weighted sum. So what value it takes? The first one is 0, 1. It happens with half. The other one is 1, 2. Happens with 1/3. The next one is -1, 1. Happens with 1/6. Overall, I will have 1/6, 3, 4. 4 divided by 3. So that's the expectation of this random vector. However, if we look at just x2, okay, I can just look at x2, the second component of x. I'm asking you, is x2 random or not?
Yeah,
it's random. Why?
It takes 3.
Okay, good. Right, just follow my kind of language, right? It takes multiple values. Let's say what value it takes. What value it takes?
1.
What x2 takes? What possible value x2 can take? 1 and 2. Are you with me? You look at the second coordinate. It's only possible for 1 and 2. What's the probability of x2 at each of this number? What's probability of x2 equal to 1? Equal to 1, it has 2 cases, right? Equal to 1, either x1 is 0, that's half. The other case is also 1. So you need to sum them together. What is it? 2/3, okay? What about 2? 1/3. Okay, so x2 take 2 possible values. Each of them occurs with 2/3 and 1/3 respectively. Okay, so can you compute expectation of x2? Okay, what is it? 2 values, 1 and 2. 1 occurs with 1/3, so 2/3. The other one 1/3. It is 3/4. This guy is nothing but this guy. The same thing, right? I prove it for you for the simplest case, but in the most general case, it's exactly the same. I just have to give you the short path, otherwise we will not be able to move anywhere. So I hope after the example, you feel comfortable about this. Okay. And you get used to more about this random or expectation. Are you with me? What time is it? Okay. Expectation, as I mentioned, Kalman filter is a conditional expectation. We are doing this, and the derivation of this involves expectation. I need to know some property about expectation. One of the most important property is the following. Expectation is linear with respect to multiplying by a constant, determinate constant matrix. Okay. So I will say this formula, can you explain this formula to me? Expectation of A times X equals to A times expectation of X. This when A is deterministic. Okay, I will say if A is deterministic, you have to make sure A is deterministic. A is not a random variable. Can you prove this? I can ask you. In the final exam, I'm going to test you a lot about probability. Okay, that's the foundation for you to learn Kalman filter. I'm not going to ask you write down Kalman filter formulas. It doesn't mean much. Okay, you have to understand it. So I'm asking you to prove this. How do you prove this? By definition, that's right. Okay, so you should at least write this word. By definition, you can get some credit. You just need to do the expectation of this. Okay, so and whenever you see expectation, it's nothing but a integration, right? Integral. So expectation of AX is what? So AX is a random variable, right? A times X as a total variable is random. It takes multiple values, right? Each of them occur with certain probability. So A times small x, all the possibility come from the randomness of X. A does not introduce additional randomness because it's a deterministic constant, right? So times the likelihood this random variable takes small x, dx. The value it takes times the likelihood this value occurs. That's the expectation of A times X. So when you see expectation, it's just integration. Oh, because A is not random, so A is independent of X. So it's like a 2 times X, right? Because integration has a linearity property, so expectation will have it. Because it's nothing but integration. Sum of all this is weighted sum. So it's just this dx, so A times EX. All right, by definition, they are the same. More generally, you can say AX plus BY equal to A times EX plus B times EY. So provided if A and B are deterministic, matrices, okay? Deterministic means it doesn't matter whether it's scalar or vector or matrix. You just take one possible value. That value may be scalar, maybe vector, maybe a matrix. Okay. So now you start to see some kind of derivation that we're going to use quite a bit in the future. But I hope you somehow are confident or feel comfortable with those notations now. Okay, let's say I wanted to compute expectation of AX plus BY. And I know expectation of X is this, expectation of Y is this. So plug in the formula, you will get EX plus BY is A times EX plus B times EY. Okay, all the linear algebra start to come into play. So that will be 0, 1, 1, 0, 1 times EX 0.5, 0.25, and the EB is 1, 0, 0, 0, 0, 1 times EY, which is 0.1, 0.2, 0.3. I forgot what number I calculated before. It should be quite simple. Let me see. I need to find it out. Okay, it's nothing but 0.85, 0.55. Okay. Okay. So it's very simple. It's just, but you need to know all the story behind it. Okay. What we have learned so far? What is probability? What is conditional probability? What is random variable vector? And how to compute their expectation? Any questions so far? No question. Very simple, right? Now we start to enter the true business. Okay? Try to do conditional expectation. Before that, we have to understand, conditional expectation is always about two things. One variable relation with another variable. Okay? So you have to understand how to describe the joint distribution of the conditional, of the two random vectors. Jointly distributed random vectors按哪个？是reset 吗？还是按？好像确实没电了吗？等一下啊，它是不是没电了呀？你看一下，那怎么用啊？没电了，没充电。
没电了。
你有这个口吗？
这个开着的吧？
对，这个开着的，看一下，看一下，可以。开着的，对，OK。Suppose now I have two random vectors. To confuse you even more, these two vectors may not of same dimension. Does this bother you? Whether it's Rn, R2, R3, R1, it doesn't matter, right? It's just the value it takes is just a vector or a number. Okay, I have two vectors, x and y. Okay, and these two vectors, the likelihood or probability behavior of these two vectors together is completely determined by the so-called joint 联合条件，联合概率，对吧？ Joint density function. Okay, so x and y jointly distributed as fx, y. So this is nothing but approximately like a probability of x equal to small x and y equal to small y. You can just think this way, but mathematically there's some kind of things for determine for continuous random variable. All right. And when you compute probability, so let's say probability of x and y, this random variable, belong to a certain set A, is nothing but integral of the joint density function dx dy. I typically just write one integral symbol. I don't repeat them. Okay, they could be multidimensional, could be simple, one-dimensional. You may ask, actually, some of you may ask, what about? So this is actually the same as if I put them together. It will become a big random vector, right? So if you want to specify the probabilistic behavior of that random vector, all I need to know is the density of that random vector, right? So that will be fz, z. So you know this z is nothing but small x and y. Anyway, we can view them together as a single big random vector. The reason we break them up is x and y has some meaning that I want to understand their relation. That's why I break. Okay, so I say I have a 10-dimensional random vector. Okay, I have a density function. But the first half means something. The second half means other things. So I want to study their relation. So that's why we'll have this joint. Mathematically, they're the same. But when we try to understand it, we want to understand them separately. Okay. And now I think all of you have learned this marginal density, 这叫那个边缘概率是吧？ Marginal density is x equal to small x. This is y equal to small y. How do they compute? How do you relate your marginal from your joint? It's just you integrate out your y. Okay? So this is nothing but equal to what? Summation of probability of x equal to x. You care about what's the probability of x equal to x. But when x equal to x, y is random. Y can take multiple values, but you don't care about y. So you sum them y equal to small y and sum over all possible small y, you got the probability of x equal to small x. Okay, and this one is the same thing. You integrate out one variable, you get the marginal of the other random vector. Let's quickly have a, I think this is the same example, right? So I want to say, this is a random vector, but I can also view like them as a joint distribution of x1 and x2. So the marginal, let's say marginal, we have computed before. Marginal for x2 is what? So x2 can take two values as we discussed before. It's called marginal, sorry. This is the marginal density. Marginal for x2 is just you only care about x2 as a random variable. Okay, so x2 can take 1 and 2. Before we say this is what? I forgot. Is 2/3, 1/3, right? So this is 2/3, 1/3. And how did you compute them? You sum over all the other y's, because when x2 equal to 1, there's two cases. Y can be, not y, sorry, x1 can be 0 and -1. You sum them together, you get a marginal for x. That's exactly what this formula is doing. Okay? So next time we'll start talking about conditional expectation and conditional densities. And that's it. That's everything we need to know for deriving common filter. All right?